Welcome to homework.
So in this question, we have been given the state of the strain at the point on the pen leaf that has components strain acting on the x direction that is equal to 200 into 10 raised to power negative 6. Then we have the strain acting in the y direction that is equal to 180 into 10 raised to power negative 6, right? And then we have gamma sub xy shear strain that is equal to negative 300 into 10 raised to power negative 6. Right now, we are required to use these values and find the in plane strains, right? So the other thing that tells us is the angle at which this element will be oriented, right? So let's start with the solution of this question. The solution is very simple, right? It's very direct. There is nothing complicated in this question. Right now, we have been given the angle at which this element it will be oriented, right? And it's given to us that this angle is 60-degree um, counterclockwise, right? It's counterclockwise. And since we agreed in the theory of this chapter, right, that we will take counterclockwise angles as positive, right? So theta is equal to positive 60 degrees. Now, we need to find out that the normal strain, right, the normal strains that are acting in the x and y direction, right? Along with that, we need the value of the shear strain that is gamma sub x sub y, right? So for that, we are going to use the equations um, 10.5, 10.6, and 10.7, right? First of all, what we are going to do is that we are going to use equation 10.5 and find out the strain that is acting in the x direction, right? So the strain that is acting in the x direction is given by epsilon sub x dash, right? And it's equal to the strain acting in the x plus the strain acting in the y divided by 2. Plus over here we have the strain acting in the x negative the strain acting in the y divided by 2, right? So it's multiplied with cos 2 theta plus over here we have gamma sub xy divided by 2 times sine 2 theta, right? Now you have all of these values, so you just need to plug them in and you will have your value, right? So that is 5.5096 into 10 raised to power negative 5, and that is approximately equal to 55.1 into 10 raised to power negative 6. Right, so let me write it a little bit nicely. So that is negative 6. Right, now that we have the value of the strain that is acting in the x direction, so we are going to use the equation 10.6 and find out the value of the shear strain. Right, so the shear strain, right, it's given by gamma sub x sub y divided by 2, and it's equal to negative of the shear acting the strain that is acting in the x direction negative the strain acting in the y direction divided by 2 times sine 2 theta plus gamma sub xy divided by 2 times cos 2 theta. Again, you have the values, you just need to plug them in. So this would be equal to 0.6334 into 10 raised to power negative 4. Right now, notice one thing over here, that this value is equal to the gamma sub x sub y divided by 2, right? So it means that this 2 is need to go over there, right? So when you shift it over there and then multiply it with the calculated value, you get that's equal to 133 into 10 raised to power negative 6. Right, now that we have the value of the shear strain as well, so we can find out the value of the strain acting in the x direction by using equation 10.7. sorry, the strain acting in the y direction, right? Using the equation 10.7. So this equation is similar to the one that we have used above, right? For the x direction. So the strain acting in x plus the strain acting in y divided by 2, negative the strain acting in the x, strain acting in the y, negative divided by 2 cos 2 theta, negative gamma sub xy divided by 2 sine 2 theta, right? So just calculate it, and we get that's equal to 3.249 into 10 raised to power negative 4, and that is approximately equal to 325 into 10 raised to power negative 6, right? Now that we have all the values, we just need to sketch them out, right? So let's take a look at that. So as you can see over here, this is a figure A, right? And in this figure, you can see that it is showing the original element, right? Now, as you can see that in this figure B, right, this element, it has been oriented to this new angle. I'm not sure that you can see it properly or not, but it is written that theta is equal to 60 degree, right? And it has been oriented in the counterclockwise direction, right? Um, and this is the new oriented sketch of that, of this question, right? Now in C, you can see that how the strain has deformed the element, right? Now as you can see that this um, dotted line shape is the original shape of the element, right? And when the strain has been applied to this element, it has deformed its shape like this, right? And that is in the dotted form. And sketch now, I your answer for this like question is part D, right? The sketch D, because it is the sketch of the whole question, right? It is a complete sketch, but I have like drawn three sketches separately so that you can completely understand that what is going on over here, right? Now one thing to remember, um, the question till here is complete, right? But there's something that you should remember. It's a key point, right? So the positive normal strains, right? The positive normal strains in the direction, it means that some elongation is going on in the particular directions with which they're oriented, which with they are related to, right? That is the strain acting in the x and the strain acting in the y direction, right? And the negative normal strains, they means that there is some compression in that direction. Now, if you come towards the shear strain, right? So same is the case with the shear strain, that positive shear strain means that there is counterclockwise deformation, right? And if the shear strain is negative, so it means that there is clockwise deformation, right? So these are the four key points that you must remember, right? But as per your question, it's completed till here, right? So thank you very much for watching the video.